Thank you very much. And what we'd like to do is talk a little bit about some neutron imaging. So this is just a little bit of background on this section. But what I'd like to do is just talk a little bit about some of the basics of the technique and then talk a lot more about some of the applications. So the basic approach here is this is really being used as an imaging or a radiographic technique. On the top you can see an X-ray radiograph, and I think we're all used to those, and we've seen a really good talk earlier today on some X-ray imaging. On the bottom is a neutron radiograph of the exact same camera, and what you can really take away from this is the X-rays are really based on density, as David was mentioning earlier, where neutrons are really based on how the beam interacts with the nucleus of the material. So different elements have a different response, and as we'll see, neutrons themselves are very sensitive to hydrogen, and because they're very sensitive to hydrogen, it gives a great way to really start tracking things like water in these systems. So the basic principles of the technique, there's a source, there's some source of the neutrons. This can be a reactor, and a lot of the really powerful ones around the world, whether it's Paul Scherrer Institute or NIST, there's a reactor there. There's also a collimator, and the collimator is there, if you think about it, it's getting all the neutrons going in the same direction. So maybe ACI needs a collimator as everybody comes in and getting everybody going the same direction as they come in, but it's basically to align the beam. That goes in and it interacts with the sample. So here you can see the sample in this particular image is a plant. We're going to do something more exciting. We're going to talk about a concrete sample, but the basic idea is that the beam is going to interact with that. And then it's going to interact with the detector. We'll commonly say that this is a picture, but it's actually a detector, and it's detecting the neutron beam that's made through the sample. So as we look at this, there's a couple different types. Here you see PSI's version of this, where they've got a great big reactor over here, and then the beam travels down, and you can place your sample in the system over here. This happens to be the neutron center at Oregon State, where the reactor is a controlled reactor here. This beam comes down and travels this path here, which is the screen line. We happen to have an environmental chamber set up so that we can control relative humidity and temperature, as well as CO2 in this path. We've got the detector here, and then we've got a neutron beam stop that basically prevents the neutrons from exposing or radiating anybody else in the system. This is that chamber that you're seeing. The really important part of the design of the chamber is we try to minimize the losses going into or out of the chamber, so we have a really clean beam. We've got the scintillator on the back, which is part of the detection system. This is what happens if you look inside the system. What you'll notice is this is the business part of this will actually connect to the detector on the other side. But the basic idea here is we've got a movable XY table. We also have a rotational stage so we can move various samples around while the beam is on, so that we don't have to keep opening and closing the chamber, waiting for the radiation to die down, and then go in and move the samples around. So again, this is just a bigger picture of what we just talked about. But the basic idea here is we have a beam. As we mentioned, we really want to try to collimate the neutron flow so that it's all really moving in a very parallel fashion. That beam interacts with the sample, and as it interacts, the beam has the opportunity to do one of three things. It has the ability to pass through the sample and be reached by the detector. It has the ability to be absorbed as it hits the nuclei. It has the ability to be deflected. So the basic idea is we're going to either see absorption, deflection, or we're going to see what's passing through. What we're actually imaging is the difference between the beam we started with and the beam that passes through the overall sample. So now we'll get into kind of how this is being used in some of the different applications that people have come up with. I will mention that this is a relatively new field. I will mention that some of the earliest papers of this, you'll see papers back in the 1980s. And I will mention this first paper here because this is a great paper that came out of Cornell. Professor Hover, Ken Snyder, Najjar worked on that paper, and it's really a very interesting paper, incredibly labor intensive because every single image they took was processed on a film. That film was then interpreted, et cetera, et cetera. But there's about 140 papers total on neutron imaging of concrete. What really pushed neutron imaging to the forefront, or what pushed neutron imaging in general to the forefront, were fuel cells. So there's lots of interest in fuel cells and looking at where hydrogen was going in those systems. and there's been a lot of off-spins of that type of work. Lots of work in China by Zhang and Volker Whitman, who've done some really interesting work. They've done work looking a lot at cracking and sealers. Here you can see a crack, you see two pieces of reinforcing steel, and what you'll notice here is sort of this grayish background is the concrete. You see the crack, but you also can see water that's coming into the system, and what you'll notice is water kind of moving along the level of the reinforcement. Right? This is a very qualitative type of approach, but you can see the water as a function of time moving up into the sample, moving into the crack, and then moving along the reinforcing steel. But what we wanted to try to do was to move this from a qualitative approach to a quantitative approach, and we use something called Beer's law, and if it's Beer's law, it can't really be a bad law, right? But what I always find interesting is you'll hear people either refer to this as the Beer's law or the Beer-Lambert law, but somehow Bourgaire always gets sort of left out of the discussion here. But all three of these guys contributed to this equation. This equation is really just the beam that's passed through the sample that we talked about before, our initial beam, and then the material that it's interacting with. So there's going to be an attenuation coefficient, which accounts for the absorption and the scattering, and there's going to be the thickness of the sample. So what we really started to try to do was to say, can we think about this in terms of the cementitious system and start to do these calculations? I wouldn't be showing this to you if we didn't do these calculations. So the basic idea here is we started to identify the attenuation coefficients for the individual materials that we're dealing with. Now you can do this based on pure theory, but the one thing that really accounts for is that you have to really know your neutron energy very well, and depending upon the source, that neutron energy can be different because of the length or the temperature of the neutrons that you're using. So we actually get this at each of the facilities that we would use. We calculate the attenuation coefficient simply by putting a known volume of that material in front of the beam and measuring what goes through the system. So this is an aluminum cuvette from the top. This, you can think of it as basically a series of stairs, right? And we pass the beam through the sample, and we can see this is what 1 millimeter of water looks like, 2 millimeters, 3 millimeters, 4 and 5, right? And if we do this, we get a relationship between the attenuated signal and the thickness of the water, and we can calculate that attenuation coefficient. One of the really fun things about, because this is so sensitive to hydrogen, this is conventional water, referred to as light water in the radiation world. This is heavy water, which is actually deuterium-based, and what you'll notice in the heavy water is we see a very different signal. Other than very minor issues in early age hydration, the behavior of heavy water and light water are very similar in terms of what they do in terms of the cement. So you can actually do some very interesting studies where you start to change these materials around because you get much better penetration when you're using deuterium in the system. The one caveat of this, water almost free, deuterium, heavy water, not almost free. All right, very expensive material that we're dealing with here. All right, the attenuation coefficient, so some of you will recognize that and say, I've seen something like that before. Yes, you've seen the periodic table before, but this happens to be a neutron attenuation coefficient table. I'll show you that most of the materials that we're dealing with are shown here in red, very low attenuation coefficients for sodium, calcium, aluminum, silica, oxygen. The ones that have a higher cross-section when it comes to neutron attenuation, hydrogen and chloride are two of the examples. Boron is another one that has a very high example. So what we could do is we can actually extend this and build a simple series model and essentially start to now calculate for all of the different materials that we have in our system. So we can say we can account for the water, the cement, the aggregate, the vapor, if you've got fibers, if you've got steel, if you've got other materials like that, we can put all this together and start doing these calculations. We're now working on advanced techniques where we can actually back calculate these from images and use these in things like tomographic images, and I'll show you some examples of those as we go forward. But it gives us the ability to quantify the exact amount of water with high precision at high spatial resolution. We can get down to about 50 microns. Some of the best systems in the world get down to about 10 microns. After that, you really start pushing the limits of neutron physics without doing something very special. So if we look at this, cement, water, sand, coarse aggregate, a lot of you will say, of course, we're ACI, we know what all these are. But if we look at these, what we'll notice is very low attenuation coefficients for everything except for water. So it becomes very easy to start to track what water is doing, and we'll look at this for some of these different systems. Catherine Lucero did some excellent work. She's now at the National, she's now with the Bureau of Reclamation. But she did excellent work of really starting to quantify this and really starting for the first time to quantify the movement of water through sorption in samples. Before this, a lot of people had taken these images and said, yeah, you can see where the height of the water is. What Catherine was able to do really well was she was able to not only calculate the height that the water had moved to, but she was able to say this is exactly the amount of water that's there. And one of the things that's very interesting is the absorption of water has a two-phased approach. We fill in the really tiny and the medium-sized pores very quickly, and it takes a much longer time to go back and fill in the larger pores under capillary sorption. So she was able to start to develop models that could describe how fast the water was entering the system and really quantifying this in terms of degree of saturation, which is really important for things like freeze thaw. The group in Switzerland, Pavel Tivik, did some of this work. At the top, this is a lightweight aggregate that was dry, jammed into a cement paste at early ages. This is a wet lightweight aggregate. And what you'll notice here is this is very early, 4 hours later, 8 hours later, all the way up to about 15, 16 hours later. If you see this turning red, that means it's sucking water from somewhere else in the system. So the dry aggregate sucked water out of the system. Right? Not shocking that this would be happening. The wet aggregate doesn't do a whole lot right when it's placed in the system, but what you'll notice is it starts to turn blue, which means it donates that water back to the microstructure. Some might even call this curing, maybe even going as far as to say internal curing. Right? So you can actually see the system suck water out of the system, which is why we have a lot of mixing problems if our aggregates aren't at the right moisture condition. But you can see this aggregate here giving substantial moisture back and curing this overall system that other than just this wet lightweight aggregate would have been completely sealed and we wouldn't have seen moisture movement. So very, very useful and very helpful in that case. This happens to be hydraulic permeability. So the common test here is you push water into a sample, crack the sample open and see how far the water went. The visual technique gives you a measure of how far the water went to get to 78% saturation. No one ever says 78% saturation. They think it's full saturation, but where you can start to detect the visibility of water is around 78%. This gives us the ability to look at the water as it's actually moving through the system, and we can actually see the increase in saturation as a function of thickness. So we can now start to quantify exactly what the hydraulic permeability of the system is. Incredibly powerful if we look at things like permeability, reducing admixtures, where we have pressure head of water that's inside of those samples. Here we're doing a technique where we're actually looking at 3D printed samples. So this is a 3D printer. We're actually now putting the 3D printer right into the beam line so that we can see what's happening as it's being printed, so we can see the water moving out from the center of the filament to the edge of the filament so that we get that lubrication layer. But the basic idea here is these were being printed. This is a sealed 3D printed structure. This is one that's open to the environmental chamber. And what we can notice here is in the sealed sample, we have slight losses of water from the sample, mostly to the surrounding environment. But we capture most of that water until we oven dry it. The one that's exposed to drying, we have an enormous amount of moisture loss. And what's really important and what's different than almost everything else we look at, for 100 years, we've dealt with curing and we've said, well, let's not really worry too much about the sample thickness because everything's thick, right? And even when we look at things like the 308 committee or we look at the bridge deck committee, we say bridges are really susceptible to moisture loss because they're 8 inches thick. These printed elements are substantially thinner than that. So when you start to look at the drying rates, it's incredibly important that those samples are properly cured. This shows that you may get only 15 to 20% of your cement hydrating because water leaves the system that fast if you're not paying attention. We can also measure things like curing efficiency. So we do a lot of work where we model the system and put it into cases like this, and Mehdi is in the back of the room, did a lot of this work, where we're able to take things like the aggregate, cement, capillary water, we're allowed to hydrate that system, and here we're simply using Power's model, but we actually use this with thermodynamic modeling, and we compute the gel solids that form, the reaction products, the CSH, calcium hydroxide, Here we can see the gel water. But what we can really start to do is quantify how these hydration products are impacting the overall porosity of the system. Now, I mentioned earlier that we can do this individually, but we can also break this down and basically say the cement stayed in the overall system, and we're just counting the additional water that went in to hydrate the cement. So all of a sudden, we can start doing things to just calculate how much of the reaction products contain water in these systems. Now, you may say, why would you want to do this? If we measure the extent of water that stayed behind in the system, we're measuring the degree of hydration. So we can actually go through and we can reevaluate these equations where we can say we're measuring this, right? We know all of these values, we know our sample thickness, so we can back calculate the degree of hydration. So all I've done here is I've plotted the degree of hydration versus the volumetric water content or the non-evaporable water, and you can see that they match up really, really well. Now some of you may be saying, wow, that's phenomenal. You've just taken a very simple test like placing a sample in the oven, and you've made it incredibly complicated. Thank you for making all of our lives harder. This would not be what I would use on the standard samples, all right? And I just got the finger from the guard, so I know I've only got 3 minutes left here. And it was a appropriate finger for any given back. But basically what we can start to do is we can say we could relate this to the degree of hydration, and as I showed, this matches up really well. But where this becomes really powerful is we can calculate the degree of hydration at specific spatial points in the sample. So here we see, all right, some folks out here, this is an internally cured bridge deck. They are all doing a great job of internal curing because you can see none of them are worried about putting a curing compound on top of the sample. All right, they're all standing here having a great time. But you can look at the curing profiles. All right, and I have to say, each time we looked at this, I was shocked at just how much curing impacts the sample. If you expose it to drying after 12 hours, you're getting about 30 to 40% of the cement hydrating in the system, where if you cure it for 7 days, that top part of the sample is getting up to 70, 75% hydration. So we've done a lot of studies, and I think Betty's going to talk about this later, where he talks about curing equivalency when you have lightweight aggregates and how you can actually get an improved curing from the internal curing perspective. So in summary, neutron radiography, a powerful technique, right? It really revolves around measuring water. There's lots of different approaches. We've seen people look at drying, sorption, hydration, curing, internal curing, permeation, curling of slabs. We've done a lot of work on carbonation penetration, carbonation depths, as well as the impact of fluid transport. Can be used qualitatively, but we believe when you start to apply Beer's law, that quantitative approach is really important. It allows us to quantify the behavior, but quantify it with really high spatial resolution, which is incredibly exciting. For that, I'd like to thank PCI 236, Professor Garth for not throwing me off the stage, and I'll turn it back over to him if we have time for questions. Thank you all.